So my second mini extra lecture is going to be about the notion of finer, coarser of a topology, right? So recall that if we have two different topologies on the same set, then we say that a topology is finer or coarser depending on whether it contains more open sets or less open sets. Right, so coarser means that it contains less open sets. So to show that the Zariski topology is coarser than the standard topology, we need to prove that the Zariski topology has less open sets than the standard topology in R2. So which boils down to showing first that every set, so every Zariski open, so Zariski open is also going to be standard open, right? So standard open. So if it is open with respect to the Zariski topology, then it is going to be open with respect to the standard topology in R2. So remember that we are talking about R2. Okay, but closed, well, when we talk about Zariski topology, it is more convenient to work with closed sets because Zariski topology is defined in terms of closed sets. And since closed sets are just complements to open set, it means that it is the same thing as to show that if every Zariski closed is also going to be closed in the standard topology. Okay, but then what is a Zariski closed set? So Zariski closed set is by definition the solution set of some polynomial equations. Maybe I'll give you some examples. So something like x squared plus y squared minus 1, that's a polynomial, so we equate it to 0, and the set of all x and y satisfying such a polynomial equation is Zariski closed. So maybe let us look at some examples. So x squared plus y squared minus 1 is 0, is geometrically a circle. So this circle is going to be Zariski closed. So here is another example. So let's say our polynomial is something like x squared minus y is 0. Okay, so this parabola is also Zariski closed. So maybe x minus y is 0. Again, that straight line is Zariski closed. X minus y squared, maybe x plus y squared is 0. So this parabola is Zariski closed. Okay, so all sorts of polynomial curves are Zariski closed. So even probably something more complicated like xy plus y cubed minus 4 is 0. Okay, something like this. All right, so this is Zariski closed. Well, and it is kind of clear from here that, okay, so maybe x square plus y square equals, I don't know, 100. Now, if you look at the intersection of two polynomials, so then this is also Zariski closed. So, and the intersection of, well, the set of simultaneous solutions of two polynomial equations is going to be just, of course, a collection of a few points. So 1, 2, 3, 4, 5 points here. So this 5-point set is also a Zariski closed set. But you see that, yeah, indeed, it is true that all such closed sets with respect to the Zariski topology, they are also closed with respect to the standard topology, like in real analysis 1. So they're kind of usual common sense closed sets. Yeah, maybe if you wonder how to prove it rigorously, that something like this, like a solution set of a polynomial equation is Zariski closed. This is simply because, you know, if you consider a function from R2 to R given by the equation f of xy, so f of xy equals this xy plus y cubed, well, any polynomial equation, then this would be a continuous function from R2 to R. So its the solution set of this polynomial equation is just by definition the pre-image of 0 under this function, and the pre-image of a closed set must be closed, right? So it makes kind of sense. This is a rigorous proof of the fact that this is a closed set. Well, so which means that since every Zariski closed is also standard closed, it means that this Zariski topology is either, well, coarser than the standard topology, or maybe it is the same as the standard topology, right? So, but now the question is it strictly coarser or is it the same? And to prove that it is strictly coarser, we need to show that there exist Zariski, that there exist closed sets in the standard topology that are not closed in Zariski topology, right? So there exists some set that is closed in the standard topology, standard closed, but not Zariski closed. So not Zariski closed. Now, I am not going to prove it rigorously that something like this is indeed standard closed but not Zariski closed, but something like a solid circle will work, or maybe like interior of a parabola. So for instance, if instead of equals 0, you take, I don't know, bigger than or equal to 0, so this is the exterior of a circle, this is the interior of a circle, or maybe something like this parabola, something like interior of a parabola, then this is still going to be closed in the sense of the standard topology, but is not going to be closed in the sense of Zariski topology. Now, I'm not going to prove it rigorously that this is not closed in Zariski topology, but I think it is more or less intuitively clear, because closed sets of Zariski topology are those that are solutions of polynomial equations. But of course, if it is a polynomial equation, then you have some equation in x and y, you equate it to 0, so you have one condition on two variables, so the result is going to be one-dimensional, so it is going to be a curve rather than a whole solid closed set. So a solid closed set would not be possible. So which is why there exist closed sets in the standard topology that are not closed in Zariski topology. So these two conditions, that every Zariski closed is standard closed, but not every standard closed is Zariski closed, they mean that the Zariski topology is coarser than the standard topology.